Hello, in this video we're going to be covering section 17.3, Electrodes and Cell Potentials. We're going to describe and relate the definitions of electrode and cell potentials. We're going to interpret electrode potentials in terms of relative oxidant and reductant strengths. And we're going to calculate cell potentials and predict redox spontaneity using standard electrode potentials. Okay, so a little something about potential here. All right. The activity of a redox reaction can be quantified by measuring a relatively easy property called potential or voltage. You probably typically thought about this as being voltage. It's called potential because it is the electrical potential energy. And by redox activity, what we're talking about is how likely this redox reaction is to happen, how spontaneous it would be. All right. What potential basically is, as the potential energy of electricity, it is a measure of the energy accompanying the transfer of charge. So if a lot of energy is going to be liberated, it's going to have a high potential. If only a small amount of energy is going to be liberated, it would have a low potential or low voltage. These potentials are measured in the volt unit, which is defined as a joule of energy per 1 coulomb of charge. Okay, so it's the energy that's liberated every time a 1 coulomb of charge is transferred. All right, this right here is going to be very important for you to do your dimensional analysis when you're doing problems. So keep it in mind, 1 volt equals 1 joule per coulomb. A potential reflects the driving force for the transfer of electrons between redox reactants. So the transfer of electrons requires 2 half-cell reactions. We've seen this, right? We know now that there's got to be an oxidation reaction that's going to be at the anode, that's going to donate our electrons, and there's going to be a reduction reaction that's going to happen at the cathode, and that's where we're going to be accepting electrons. And we have our phrase here. Electrons flow from the anode to the cathode. The difference in potential between the 2 half cells may be measured. These measured potentials are called the cell potentials, okay? So the voltage that's going to be produced by that cell. And if you know anything about physics or electricity, you'll know that voltage can only be measured between 2 points. Okay, so if I measure the voltage between the cathode and the anode on a galvanic cell, I'm going to get the cell potential for that cell. Now, it would be nice if we knew the potential at the cathode and we knew the potential at the anode, but we can't measure these directly without doing something clever, which is exactly what we have done. What we've done is we've started off by first standardizing some of our variables like we often do in science. Okay. And we defined something called the standard cell potential, and we put a little dot up there just like we did with enthalpy and entropy and Gibbs free energy. And this is going to be the cell potential measured when both half cells are under standard state conditions, which we're going to define as 1 molar concentration, 1 bar of pressure, and 298 Kelvin or 25 degrees Celsius. Then we can rewrite our equation before, and we can say that we have the standard cell potential is going to be the difference between the cell potentials under standard state conditions. Now, we still can't quite measure these, all right, but we got even more clever with this, all right. And so basically, to simplify the collection and sharing of potential data for half reactions, what the scientific community did is they designated one particular half cell to serve as a universal reference for cell potential measurements. Okay, so if I just define one specific half cell and then measure the voltage across that between any other cell, I can come up with a standard voltage that I can then use to compare that activity versus everybody else. Okay, so we're always measuring against a standard. That standard is called the standard hydrogen electrode, or the She cell, and it is based on the half reaction below. So it's the two protons take on two electrons to produce hydrogen gas. And this is what the typical shell is going to look like. First off, we're using a platinum electrode. That's nice because we're not seeing any kind of reactions, any side reactions with this. And we're going to pump in hydrogen gas down here. And we're going to put that in an acidic solution down here. All right. So then we have everything present in the phases that it needs to be in order to get this reaction to happen. All right. And we're seeing some catalysis happening here. Now, what makes this nice is that this basically means that we're not going to see any fouling of this electrode, which is a little detail your book doesn't really go into. But typically when we have an electrode and we have either mass being lost or some mass gained by these electrodes, over time they're not going to give you their full voltage. All right, other things are going to come into play and they're going to start to lose some of their activity. All right, here though, where we have these protons coming in and grabbing those electrons, all right, well, that's pretty clean with the acid versus this. We're not seeing decay of that platinum because it's not typically going to react with acid because it's so inert, all right? And because we're pumping in this hydrogen gas, we're pushing all of that hydrogen gas out from the surface there and always replacing the working medium. Okay, we're just getting rid of that other hydrogen gas that was in there, and we're controlling our atmospheric pressure by doing that as well, so that we know that we always have the same atmosphere. And this electrode stays very, very clean because everything happened either in an aqueous or a gas phase. So now what we have is we have the electrode potential for a half cell is defined as the potential measured for a cell comprising of X acting as the cathode and the She acting as the anode. So what we do is we put that She in there for the anode where things are getting reduced, all right, and we have, where things are getting oxidized, and then we always have the other cell acting as the anode, and then we measure the voltage across that. Now, this may not actually be the cathode in the sense that it's not the place where reduction is happening, okay, based on the chemical activity. When that happens, and we put it in place of the anode in this equation, what we're going to wind up with is an E cell that is negative, all right? We're still going to be able to measure it if you go and test it and you take a multimeter, you put it on a battery, okay? One way that you do it, you're going to get a positive value. You switch them over, you get a negative value. They'll have the same magnitude but different signs. So since the definition of cell potential requires half cells to function as the cathodes, where we're having reduction, we always write them as standard reduction potentials. Okay? These are all tabulated in Appendix L, and you're going to need that to solve our problems this week. Okay? Here is an example where we're testing it versus that copper reaction that we saw before. All right? I'm going to set this up in a galvanic cell, as we've seen before. I'm going to put the She cell over here. I attach my leads onto it, and I get a positive 0.337 volts. Therefore, if I wrote out the standard reduction potential, meaning Cu2 plus 2 electrons goes to copper, I'm going to say its standard potential is 0.337 volts. Now, we've seen that these standard potentials, as we measured them, okay, could be either positive or they could be negative. All right, so I could have a positive E cell or I could have a negative E cell. Spontaneous processes are going to have a positive cell potential. Non-spontaneous processes are going to have a negative cell potential. Now, since electrode potentials are for reduction processes, an increased value of E corresponds to increased driving force behind the reduction of species. Okay, so if I go look up the standard potential for a specific half cell and it's larger than another one, then that means that that species wants to be reduced, meaning that it's a stronger oxidizing agent. It will reduce itself in order to oxidize others. All right. And that's another key thing here that we have to keep in mind. This language is confusing. All right. So let's go back just a little bit here. First off, standard E cell. If I want to calculate the standard E cell, all right, I need to use this equation. All right. I need to look up a half reaction that's behaving as the cathode in my galvanic cell. I need to look up the half reaction that's acting as the anode in that cell. Both of these were measured against She cells, all right, but the She cell will not appear in my galvanic cell at all, okay? I'm just using these values as standards. I take that difference and I get the cell potential for my cell that does not contain the She cell at all, the She half cell at all. Next key thing here to keep in mind, all right? When we say this standard E here, we're talking about the standard E's that we would have looked up in Appendix L for a specific species. We're not talking about E cell here, okay? What we're saying is that when those values go up, meaning that they're less negative, possibly, or they're more positive, that means that that species wants to be reduced more, okay? If it wants itself to be reduced, that means that the thing it's going to react with is going to be oxidized, all right? So by saying that it itself wants to be more reduced, you're saying that it's capable of oxidizing something else. That's where this language comes in, okay? If I'm going to want to be reduced myself more, I am a stronger oxidizing agent to other species. The reverse is true. If I myself want to be oxidized, that means I am a stronger reducing agent to other species. All right? So oxidizing agents themselves want to be reduced. Reducing agents themselves want to be oxidized. And again, negative values for the electrode potentials are simply a consequence of assigning a value of 0 to the She cell. Okay? That means that what happened is the She cell actually was acting as the cathode in that reaction, and we wound up getting that negative voltage. Now, let's talk about reversibility here. If a process is spontaneous in one direction, it is non-spontaneous in the opposite direction. We know this to be true now, right? The potential of a cell reaction shows consequential relationship with its arithmetic sign, all right? So just like we've seen with enthalpy and Gibbs free energy and stuff, if I have a reversible reaction, which most all of these redox reactions are, in one direction, if I wind up with an E cell that's going to be negative, if I reverse that equation, I'm going to change the sign of my E value for that reaction. Other things are not true, all right? If I were to say multiply all of these by a specific coefficient to change their stoichiometric coefficients, you do not multiply E cell by that value, okay? It is true that you can add them together and then you're going to add E cells. All right. But again, if you multiply these all by the same value to change their stoichiometric coefficients, it does not work like some of our other thermodynamic quantities. You do not multiply E cell by that. E cell is an intensive property and it is independent of the size of the system.